Yes.
Okay. So this is one photograph of a data path, hardened data path, and you will notice that it is not really symmetrical for all bits, as Ranjit was saying. It is not really symmetrical for all bits, but yeah, it's fine. So we come into adders. Now, what is an adder? Or are you able to see this functionality, this truth table? Can you validate this is the correct truth table for the adder?
So what's the scary status in which delete and propagate and generate are written? Like that's the different thing.
Yeah. So अभी उसको छोड़ देते हैं. Are you able to validate the otherwise K map?
Yes, sir.
Yes.
Yes, sir.
So now let us look at the last column. What is carry status? So let us say that there was the inputs A and B were both 0. Then independent of CI, what will happen to CO? CO will be 0. Are you able to see this?
Yes, sir.
Now, if either of A or B was 1, if either of them was 1, do you realize that whatever be the carry in, it will be propagated further? Hello?
Yes, sir.
Yes, sir. Yes, sir.
And when both A and B are 1, then again, whatever be the C in, C out is definitely 1. Are you able to see this also?
Yes, sir.
So this is what we want to say, or this is what this delete. Delete means whatever be the C in, C out will be 0. Propagate means whatever be the C in, that will be propagated on C out. Generate means whatever be the C in, C out will be 1. Are you able to see this?
Yes.
So that is what carry status means. This becomes important as we will look at implementation. So a typical or a very basic implementation of this adder would appear to be something like this. That S is equal to 1. So what we do, we look at this K map and we start to say, okay, it is, oh, there is a 1 over here. No, sorry. We say, okay, my S is 1 over here, then it is 1 over here and 1 over here. And my C out is 1 over here and here. So you start to merge and you start to see if you could have K maps being used to arrive at a logic. And when you do that, you arrive at this kind of a K map. That S is 1 when either of these 4 constructs is 1. And C out is 1 when either of these constructs is equal to 1. This is how you must have done adders earlier also. This is a simple adder, full adder. Huh? Yes, now we say that, okay, in the same adder, we have used A, B, and C, and then we have used inverts of B and inverts of C and inverts of A to make our logic of S. So probably I will need a lot of gates to do it. Can I do it simpler? So we say, okay, there was this information of delete, propagate, and generate. At least that much I can use for generating carry out. So we say that, okay, we express sum and carry as a function of propagate, generate, and delete only. Where carry out can be represented as a sum of G plus PCI. P propagate, if propagate is 1, then whatever is the CI comes on there, or carry is generated. Either carry is generated or carry is propagated, and therefore CI becomes C out. And S is that my propagate should be 1. It's a XOR of propagate and CI. In fact, just to make our logic a little simpler, use lesser number of devices, many times you will use propagate as A or B. Because in A or B situation also, whatever is the Cn, whenever Cn is 1, you will propagate that. Are you able to see this? See, for C out, I already have G there. That is, if A and B both are 1, I will have G equal to 1. So if Ci was 0, in that case also, I could say that, let me use propagate as 1. Because C out will be given as 1 from here, generate part itself. So many times, just to make your logic simpler, we may want to use propagate as A or B instead of A's or B.
Sir, but this A plus B, we could have said this from the truth table also.
From the truth table, it is not really A plus B. Look at it. If it was A plus B, then
and 1 would also result in the
yes,
propagate.
This would have resulted in propagate, but this has resulted in generate. So it was only propagate here, and this would have been 0.
Yes, sir.
That is not the case. So in actual terms, it is generate. But even if you call it propagate, it doesn't matter, because the CO has to be generated. The CI will be 1 there. Because for generate, you have used the variable as A or B, A and B. So A and B are 1. So C naught के अंदर आपने ये डाल ही दिया already. Are you able to see this? Yes.
So can you please, like, I got confused in this part, why we are using two expressions for a propagate?
So you use only one expression, A or B.
Okay. So, but why we are using two here?
Sorry?
I understood your point that I can use 1 and I'll get the functionality done. But why 2?
Why to do it?
Why 2 values of propagate? 2 expression for propagate.
See, the exact expression is A or B.
Yes, according to the truth table.
But we said that even if we use the expression of A or B,
yes, sir,
C naught and S will not be different given this expression. G is equal to C naught is equal to G plus PCI, and S is equal to P's or CI. So these two outputs will still remain same even if I use propagate as A or B. But OR gate is much simpler than a XOR gate.
Yeah, yes, sir.
That is why.
Okay, thank you.
Sir?
Yes.
Sir, here it is written can also be expressed by sum and carry out can also be expressed in terms of D and P.
Yeah.
But I think instead of using D, if we use G, it would be more, I think when we will implement by using D, 2 more inverters would be required, right?
You see, you will need inverts of A and B, yes, but just work it out. It is not saying this is the minimum, the one with D and P will be the minimum gate implementation. It simply says if you have D and P available with you, even then you can implement S and C naught.
Okay, sir.
What it essentially intends to communicate is you need to do either of generate, you need to do either generate or kill. Don't need to do both.
Yes, sir. Yeah. Yes.
So even though we want to express sum and carry as functions of P, G, and D, P and either G or D will work for us.
Yes, sir.
Okay, that's the intent over here. So now that was 1-bit adder. If we have to make a 4-bit adder, what do? We simply say, okay, this C out of bit 0 is C in of bit 1. And C out of 1 is C in of bit 2, and so on. So what happens? Once the C out of 0 is generated, it goes as C in of the second full adder, then third full adder, then fourth full adder, and then you get the output. So what is happening? I'm rippling the carry from one full adder to another. And what is the worst case delay? If as I increase the number of bits, the number of hops increases linearly. And therefore, this is order n. And what we also understand is that carry in to carry out path should be as fast as possible. Are you able to see this? These two aspects?
Yes, sir.
So now, if we go ahead and try to implement that full adder, which this functionality in terms of a CMOS logic, you would get a 28 transistor implementation, something like this. So you can do it at your own leisurely time, where you will see that this is G, A and B, and then this is C and A or B. So this is your C out, and similarly you will get your sum also based on by implementing whatever logic we had given there. Is this clear?
Yes, sir. Sir, in the last slide, I have a question.
Yes.
Sir, here T adder equal to n minus 1 T carry plus T sum. Sir, this T sum, shouldn't it be maximum of T sum and T carry?
Exactly, sir. I do have the same understanding.
So let us look at this path. What happens? You realize that A, B, and everything was stable already. These parts were stable already, is it not? When your carry came, what was required to be done? When your carry came, you only need to evaluate these parts of the gate. है ना?
Yes, sir.
Yes, sir.
So, and you notice that CI has been kept as close to the output as possible so that the delay from C to out is minimum. That is the delay mentioned as C sum or T sum. Whereas from A to sum or B to sum, the delay could be slightly higher.
Okay, so already we have decreased the delays internally from carry to output.
From carry to, yes.
Okay.
So there is a different delay for generating a carry. That is evident because delay to generate a carry is this path. Delay to generate a sum is this path. You know?
So sir, this sum depends upon the voltage at node X, which is also one of the inputs. So it constitutes this entire path from X till S. So
yes,
that can cause more delay for S than C out.
Okay. Yeah, can. Okay. So what is also now important to see is that if you have a adder, then you could actually have a invert adder also there. So what has happened over here? You have a full adder. Over here you have inverted all the inputs, and you say, okay, your outputs will also be inverted. So S bar of A B C I is equal to sum of A bar B bar C I bar, and so on. By using this inversion property, what do? You say, okay, I will at least not use this inverter. This one we may have to use, but at least जो C not जो C out generate करने के लिए inverter है, I can avoid using that, and I would have C out going directly to the inverted full adder. The next one I will have a regular full adder and then again an inverted full adder. So if you do it like this, then what happens? The total number of transistors in your system reduces. Because you don't need to put those additional inverters at the end of it. So there are two things that are evident, that there is a focus on reducing delay, and then there is a focus on reducing area also, because this is a large number of devices, 28 transistors. So we want the delay to be less, but we want this number of devices also to be less. So that is where figures in this mirror adder, where you will see that the NMOS and the PMOS parts are kind of mirrors of each other. And again, the circuit works fine, where you say that, okay, you give CI from here, and you get Cout bar, and you get S bar as outputs there. Okay? So you can, at your own leisure, evaluate that this works fine. This is fine for the functionality that you want to achieve for both C0 and S.
Sir,
Okay.
but this particular topology will be valid only if we have even number of stages, right, sir? If we have odd number of stages, then once again we need to add inverter at some stage.
That we can just add on the last inverter, no? Last stage.
Yes.
So just one inverter will come. It will not come 25 times.
Yes, sir.
So that we can always terminate appropriately. That's
Yes.
simple. Okay, na? So what are we talking about? So for the mirror adder, for example, we are saying that what we've done is the NMOS and PMOS stacks are completely symmetrical. They are very similar to each other. And I think from the discussion that we have had till now, you must have already realized that the load on Cout, or the capacitances linked to generation of Cout, should be kept as low as possible. Why is that? Why should the capacitances linked to generation of CO be kept as low as possible?
Because the carry has to propagate through the stages of adder.
Yes, because the carry out of your stage will go to the next stage, then again the entire carry out will be, new carry out will be generated for the next stage, and so on, at least if the propagation is going to happen. So that is what we are looking at, that we have to reduce the capacitances also, we have to reduce the delays. As you reduce the capacitances, power and delay will automatically reduce. Is that clear? Okay. Then see, we looked at that. What we looked at just now was a ripple adder, where data would move from carry out would move from here to here to here, finally giving a carry out 3. It's a very long path. See, the sum path is very short, but Cout path is very long, especially if you have large number of bits. So you will see that in the next few slides, we're just talking about how to anticipate the carry. So one way is bypass the evaluations of Cout for all these stages. Simply see if the overall P0, P1, P2, P3 are all 1. If they're all 1, then what you say is that, okay, since all the propagates are 1, then whatever was there on CI will definitely come on Cout also. Are you with me? Any questions?
So we are saying if all the propagates are 1, so the input carry will be reflected at the output directly.
Yeah.
That we have studied. Okay. Yes.
Hai. So if we do it like that, then what happens? We have carry bypass for first 4 bits. Then we have carry bypass for the next 4 bits. Then we have carry bypass for the next 4 bits, and so on. So if there are total number of m bits, then what is the total delay of the adder? You will see that the total delay of the adder would reduce would reduce such that you will have n divided by m minus 1. So the total number of delays that you will now need to see is, what is the critical path? The critical path would be something like this. है ना?
Sir, would the largest delay also decrease?
Yes. The largest delay. Yes, it would decrease because earlier, like it would decrease if you're using the propagate and kill wala topology, because if you are not using propagate and kill wala thing, then what happens is that all A, B and Cn will be calculated from top bottom, and then you will arrive somewhere at sum and carry out. However, because you're using propagate and generate thing, you already know what the C out could be much faster. You don't need to evaluate after this comes. You know what is the status of P and Z, the multiplexer inputs are already set, and you either propagate or you generate. So it saves time. We'll see how it saves time further also. But this saves time because now your ripple is only for m number of bits. So you see, initially it appears that when the total number of bits is very less, a bypass adder, because of its more complex logic and a multiplexer in there and so on, may take a little extra delay. However, when you're talking about large number of bits, say 32, 64, 128 or so on, then ripple array is much slower than bypass adder. And it is a consequence of these equations only, nothing else. Okay. Any questions?
Sir,
Rajneesh?
sir, in the previous slide, sir. So one slide back.
Yeah.
Can you explain this n by m minus 1 t bypass term once again?
Okay. So let us say this is 16-bit adder, है ना? This is 16-bit adder. How many bypass would it take? Would it pass through? So first, before that, how many bits? How many bits in one stage? 4. Hello?
Yes, sir.
So if you have a data adder coming or set of inputs coming from here,
Yes.
this is while this is being evaluated, this part of data would have already been ready.
Yes, sir.
Similarly, here things would already be ready.
Yes, sir.
So when you want to find the total delay, what are you looking at? Setup delay plus carry generation delay plus number of these that will be there, n by m minus 1. So actually n by m minus 1 hona chahiye kya? We can see. So we know that, okay, 16 bits have been split into 4 bits each. So we would have 4 minus 1.
सर मतलब n by m तो एक में बिट एक पैरेलल पाथ में बिट होगी ना सर, n by m.
हाँ. T bypass is the delay of, let us say, this multiplexer.
सर पहले वाले के t कैरी को स्किप कर दिए इसलिए n by m minus 1 कर रहा है.
Yes, because यहाँ का तो t कैरी पूरा का पूरा जनरेट का ही आपने लगाया.
Yes. Yes.
Sir.
Yes.
Sir, in case in all the bit 0 to 3, 4, 7, 8 to 11 and 12 to 15, if this condition is not satisfied that P0, P1, P2, P3 is equal to 1, then in that case, none of the carry would be directly going without facing the carry propagation delay.
See, if if the propagations are not all ones, if the propagates are not all ones, then what happens? then you anyway you will not be rippling the carry to the entire path. So your overall delay will actually be lesser only. Whatever was evaluated here earlier would already be valid. We are talking about the worst case delay, where you say, okay, the ripple has to happen through the entire system. Because if there is some P and G equal to 0 at some bit, whichever bit it is, then it means that the evaluation that was done for higher bits than this were already clean, because Cin was anyway 0 and it will remain 0. It will not change it.
Okay. Yes, sir.
So as you increase the total number of bits, you see that bypass adder has much better performance than ripple adder, but it has much more circuit also in there to be able to do all these. So there is a multiplexer, there is a setup circuit, and so on, which would be there. Ranjit, you have a question?
Yes, sir, in the previous slide.
Okay.
Sir, I understood how we get the T setup, M times the T carry plus N by M minus 1 times the T bypass. But why once again we have M minus 1 times the T carry, sir? This one I didn't understand.
Okay, so wait, let me show. The variables are different. थोड़ा सा ध्यान से देखो. This variable is M T carry, and this variable is M minus 1 into T carry.
Okay. But why M minus 1 into T carry, sir? That I didn't understand. Because always, if we consider one single bypass stage, the carry generation will happen parallelly for all of them. So, and then we'll bypass this particular.
For the first stage, that carry generation, you have to still count. Na? एक बार तो you will have to count.
Okay.
Then you add the delays of various ones. And for this one in itself, if there are M bits, then that would mean M minus 1 times ripple could happen at least in this one, is it not? Even for a 4-bit thing, if the carry has to be generated like this, there will be 3 ripples happening inside it, is it not?
Yes.
That is why.
Okay, sir.
Hello?
Yes, sir.
Okay. So, is it clear till there? Ranjit, your hand is still raised. Anything pending there? Okay. So, this was where we were actually using the carry to reevaluate the circuit and arrive at an output. If we are ready to give area, then another idea could be assume that carry could be 0 and assume that carry in could be 1 and calculate C out for both the cases. Depending on the value of C out of K minus 1 stage, that is the C in of this 4-bit circuit, you can choose whether this one has to be used or this one has to be used. In this case, carry calculation is actually happening completely in parallel, and you're just having a multiplexer at the output stage. Are you able to see this? So in other parts, we were simply doing one circuit which was doing generate, propagate, that kind of function. Over here, we said, okay, all that generate, propagate, you do it for both Cin is equal to 0 and Cin equal to 1. Depending on what was the value of Cin, I will choose the output directly at the multiplexer stage. So now even if you go to 128 bits, all will run in parallel. And all that I need to do is the previous stage output goes as Cin over here, or goes as multiplexer input over here. So the delay is reduced further. Look at this example. What we say, bit 0 to 3, I calculate the output with 0 carry, I calculate the output with 1 carry, and then I use the carry in as the select signal for the multiplexer. And I will get the sum generated and I will get the CO3 also. And the worst case critical path is as marked over here. Are you able to see this? Any questions? No questions?
So, so basically, you are breaking the adder 2 times for each stage, and then you are letting the other stages evaluate according to the carry equal to 0 and 1, and then you are selecting based upon what is the carry that you get from the previous stage.
Yes.
So doesn't this architecture result in exponential rise in the area consumption?
Yeah. Area to badi raha hai. Definitely. Instead of just one carry, one evaluation circuit, you're putting 2 evaluation circuits, one for carrying equal to 0, one for carrying equal to 1.
Yes,
but the delay is also reducing.
Okay.
So if we look at it, slightly more advanced versions of this. So over here, notice we're talking about S0 to 3, S4 to 7, S8 to 11, S12 to 12 to 15. In a more advanced version, when we have it as this, then this is what my total adder delay is: setup plus n by m into t carry plus m into t mux plus t sum. So this is what you would get as the overall delay of this system. However, another interesting way is you say that, okay, over here there are only 2 bits. Over here there are 3 bits. Over here there are 4 bits, and so on. So I'm gradually increasing the total number of bits that this system is taking up. Why am I doing that? Why am I increasing the bits?
Why is the concept of logical effort? At the end stages near the output, we increase the size so that we get the optimal deal.
Not exactly. So the output is the S0 and 1 are also outputs.
So basically,
S14 to 19 is only MSB, most significant bit wale outputs, but S0 and 1 are also outputs. Ranjit, you're saying something?
No, sir.
Sir, so number of mux.
Yeah, what about number of mux?
So they would decrease. So the value of in the previous slide, empty mux would decrease.
Yeah, see what is happening is, you know that, let us go to the previous slide. You know that to arrive at this stage, I will go through not only this, but also this horizontal delay. Are you able to see this? So by the time this C0 and C11 comes, C output 11 comes, I would already be waiting at the input of the multiplexer. So I say, why wait? Instead of calculating a ripple across 4 bits only, I actually have more time now. So I can calculate ripple across 5 bits or 6 bits. And when you do that, what you achieve is that even though you are rippling across 5 or 6 bits here, because they are most significant bits or close to the most significant bits, the select signal anyway would take a long time to come here.
So it's like time borrowing from.
It's like
Borrowing the time, basically.
Yes, you're using the extra time that is available to you because these extra multiplexers are also in the path and adding one more stage there, let us say. Not stage, one more bit in this kind of a setting. And this is how the delays change. See, this is ripple carry, this is linear select, and this is the last square root select that we just did. So you will not see much difference at the lower number of bits. But today, as we are talking about 64-bit processors and then probably 128-bit in a little while, then you will see that this part at more number of bits, square root select or linear select adders are much faster. So you can choose which one to use. Okay. Is it clear till here?
So I had a very small doubt. I think the 2 slides before, can we go? Previous 2 slides. Sir, in this, why don't we make the 0 carry and 1 carry adder parallel to each other and then give those inputs to mux? Or
So they are in parallel. Notice.
Okay.
Setup is going here and setup is going here also in parallel.
Oh, so they are shown like this. Okay, got it.
They are represented like this. They are going in parallel only.
Okay, got it.
Okay.
Thank you.
Yeah. So after the carry select adders, you must have heard about what is called as carry lookahead adders also. So what do carry lookahead adders do? They do something similar to this select thing, and they say that as you go into the higher bit, there will be more time, and therefore you could have a longer path set in there. So what is the idea behind it? You say that, okay, to be able to anticipate the output over here, I don't need to wait for ripples or even inputs to come from this side. Let me at every gate itself, use, the earlier gates iteratively. So look at it over here. We are saying C out 3 bar is dependent on generate 0 to 3 and propagate 0 to 3. Now you do not need to see what propagate 1 was and whether the carry would go from propagate 1 to propagate 2 and all that. You don't need to see all that. It is already inbuilt into your one complex gate. And you could have C output there right away. Okay? So that is what look ahead topology looks like. You see, what we do then what we see is that C0 is G0 and P0, Ci0, but CO1 is equal to G1 plus P1 G0 plus P1 P2 P1 P0 C0. CO2 is equal to G2 plus P2 G1. So basically, you are kind of continuously recursively adding the delays there. And what do you see? You can continue to build a tree kind of hierarchically. So what does this mean? This means that we're talking about, how do we put it? We're talking about these adder trees where A's and B's and their components outputs are used. For example, A0, B0 will only influence S0 and S1 because the carry would go there. But in terms of higher bits, we know that A1, B1 can also influence S3. So we build this kind of a tree, and there are complex trees also. See, there are two stages in this: the first stage, second stage, third stage, multiple stages in these, where we say that, my S8, S7 goes to S8, and my S7 also goes to S9 and S10, and so on. I build those trees and ensure that my overall functionality is correct. And it is because of these lots of routing connections. All these are routing connections, is it not? That in the adders, if you remember, there was adder stage 1, then wires, then adder stage 2, then wires, and then final adder. Remember that curve? The thing that we had shown. In fact, there was a question that someone asked in the chat window also. Why is there a separate region for wires? There is a separate region for wires because there are all these interconnects that have to happen after every stage. And you would rather have them done neatly by allocating a safe region for them, rather than going to higher metal layers and using the resources there. Is that okay? So again, I'm not going to ask you about make the Brent-Kung tree or make this adder tree or that adder tree. The intent to take you from this stage of ripple carry to carry look ahead to carry select and so on is so that you know that there are different ways of arriving at the same output. And depending on your project requirements, you will have to choose the most appropriate one. So, Rajneesh?
Sir, in the carry look ahead, sir. Sir, from where the G and P is coming, sir? In the 2 slides before, sir. The 3 slides.
Okay, you tell me.
सर जैसे सर फुल एडर में तो सर हम लोग का मतलब ए बी और ए XOR B किए थे.
We could always generate G and B through those AND gates. You remember the equations that we were looking at earlier for G and B?
Yes sir, फुल एडर में.
Yeah, we simply generate those.
अच्छा, मतलब इसमें भी सर सेम रहेगा वही चीज.
Yeah. So that is where that truth table में वो generate, kill और propagate वाला information was also important.